I guess it's about time. So let's get started with the presentation. So I'm Titouan Vervac, and I've been working for Sigasi for just a little over a year now. I also did a talk at EclipseCon of France about formatting your code. And since then I've been working on graphics, so how to tame your complex chip designs with beautiful diagrams. And Sigasi is a software company based in Ghent, and we're spreading like a virus. We're taking over the world. I mean, this is the countries where we ship to, where we distribute our software. And what we create is a Eclipse-based VHDL and SystemVerilog IDE as a standalone and as an Eclipse plugin. And if you don't know what VHDL or SystemVerilog is, that's okay. It will become clearer over the presentation. To tell you more about how we tamed complex chip designs with our beautiful diagrams, I have to first give you a little history lesson on digital hardware design. So our clients, our customers, they design digital chips. So those are the black boxes that you see on printed circuit boards. And if you cut off the top of such a box, then what you get is the picture to the left over here. So you have all of these metal pins over here. Those are inputs and outputs. And they connect up to the golden wires inside the chip, and those connect up to the silicon in the middle. And the silicon is just a bunch of transistors. And in the 70s, the digital hardware designers had to manually draw all of these transistors. So what they drew was here on the top. So they draw an NMOS, that's one transistor, the PMOS, that's a second transistor. And they had to draw all of those, hundreds, thousands of them, and then connect them up together with these metal lanes, here the inputs, the outputs. They have to make sure that everything fits on this 2D structure, the chip. So this chip can be seen a bit like a big building, skyscraper of sorts. And yeah, so the digital designer really thinks graphical. He thinks, how can I put all of these transistors together, make sure that they're connected, that there's no interference, and so on. So moving a few years later in time, we have hardware description languages. And those were invented because there's not just 100 or 1,000 transistors, but there's billions of them. And there's two main ones, so VHDL and SystemVerilog or Verilog. Those take up most of the market. And HDL works with entities and architectures. So an entity is much like an interface in software. It defines the structure of your design, while the architecture is like the implementation of the interface. It defines the behavior of your design. And this digital hardware designer is still thinking graphically. So what he has in mind now is this logical gate here. So this is an AND gate. It might be something even more abstract, but I'm going to tell a lie here and there just to make things more simple. And now with hardware description languages, he has to write this code. So we have an A port, a B port, both are input and both are bit. And then we have one Q port, which is an output bit. And then in the architecture, we say, okay, Q equals A NAND B. And then we take this code, we throw it through a few programs, and then it will do all of the placing of the transistors, put them on the chip, make sure there's no interference, and then we get this diagram again, with this time 4 transistors. But not every designer thought that this was a good idea. The text might help them with complexity, but they lost their graphics. They really like those because that's documentation. Now they have to open up Visio, they have to draw their own blocks, connect everything together. So that's twice the work. So now, a few years later again, they thought computers have become more powerful. This HDL has matured. We know the advantages and disadvantages. Let's go back to the old days and just do everything graphical. So here we end up with graphical editors. And these graphical editors, they were obviously much better because the navigation is intuitive. You can just click on blocks. They're very good for inspection and exploration. So I make a design, give it to my colleague, and he can immediately see what I had in mind. So it's very close to what the designer had in mind as well, with all of the layers and the blocks and stuff. And it's in its own documentation, so you don't have to open Visio to go and make your drawings anymore, because that's actually your source code. So these graphical editors, they generate HDL code, but this HDL code is transparent, so as a user you will most likely never touch it anymore. And then this HDL code is fed back into your tool flow, and the tool flow can give feedback on the code. And this is an example of such a tool, so this is active HDL, and then you have all of these blocks over here, and you click and drag to connect them with these wires. So in the top part you can see the structure, and in the bottom part you see the behavior, so they still connect up all of these blocks, but they write HDL code within the blocks. So now you have structure and behavior in one diagram. And a lot of time they're just spending all of their times on aesthetics. They're just moving blocks around so that everything looks good, so that it's readable. And then when you save your editor, you have to save the position of all of these things. So what you get is one big binary file. So a binary file, I don't know if you ever tried to diff this. That doesn't work, so you can't put this into version control. You might think, why put the binary format in version control, just put the generated sources in it. There's the same problem if you've ever used generated code. You know, one change in your source changes everything. And this binary format also creates a lock-in with your product, so I can't take this design and open it up in a new program because the binary format is not standardized, while HDL code is IEEE certified, standardized. And that's the end of the project. Okay, so it works again. And another problem with these graphical editors is that you have very complex chip designs, and there's a one-on-one relationship with your editor, so you have to draw each and everything that comes onto your chip. And then you get something like this, where you have to connect everything, where you have to use this as documentation. So yeah, putting everything into graphics and just making your code transparent was not the most efficient choice in our opinion. Another problem is that these graphics are a one-on-one representation, which means that your graphics always need to be in a consistent state to be generating HDL code. And of course, that's not always the case. And sometimes you can catch those errors and then just give feedback to your graphical view, but not all of the time, so only in the trivial examples. And the other way around, you feed all of your generated code into your tool flow, and that gives feedback on your HDL code, but you're working on graphics, so how do you get your errors back in the graphics? And do take in mind, we do think that graphical editors are trying to solve a real problem. They are trying to match the design closer with what the designer had in mind, but there's way too many issues with it, so we think there is a better way. So there's 20 years later now, and we have a fancy editor. We can analyze all of the code. Computers got so much faster. Let's just put code as a centerpiece, because code is portable, it's diffable, and it can be detailed without cluttering all of your code. But we still think the designer needs its graphical views, so we generate read-only graphical views. And then you can just navigate from the view to your code and the other way around. And there is no more need for a one-on-one relationship, so we purposely simplify the diagram so that you can use it for documentation. Sorry. And you can still use it for exploration as well, because you've got these navigation functions, as I'll show in a little bit. And now the errors are no longer a problem, because you can compile your code in the feedback loop, get your feedback, and just work with it. And we can also work with any legacy product, with any legacy code. So there's the code that was written in the 80s works in our editor. We can also use it as an intermediate product. So when you're going from graphical design to textual, you can just take the generated sources, put it in the editor, and everything will work. So this is the interaction I was talking about. On the left, you have some VHDL code. There's 4 blocks over here. And this is our read-only view. It is auto-layouted and all of that, so you don't have to worry about the aesthetics. And then when you double-click on a block, you go to the code. And when you say, please show block 4 in my view, it goes to the view. We'll show this in a demo in a bit. And you can also save this for documentation purposes, or we have some quality of life things like zooming in and fitting the diagram to your screen. And for this, we used mainly 2 frameworks from the University of Kiel. So that's ELK, the Eclipse layout kernel, which does all of the layouting. And also Klite, which does the visualization and which does all of the animation of our model. You might be thinking, why go so exotic? Why go for an academic framework? Why not just use JavaFX? Well, when we started with this project, we were still on Eclipse 3, and we also have our standalone end plugin. And it was really hard to just get one view that worked everywhere without a problem. So we had to move on. So what you might think next is Graphics. But that makes your installation more difficult because you need a third-party dependency. So let's go back to Eclipse. Then we have GEF, but that's made for editors. So creating read-only view requires a lot of modifications. So it wasn't ideal either. And then Zest, we've used that for quite a while, but we've moved those views over to Klite as well a few months ago. Ideally, we'd have a SVG viewer, so maybe Sprotty in the future. We will see. But now, is this the perfect solution? No, of course not. So over here, you have a design, and you probably can't see anything. It's way too cluttered, too much detail, no focus. And we even have clients which gave us an example of a 20 megabytes SVG file. So even Inkscape and browsers have trouble navigating through that. Like even if you turn this sideways, still doesn't make any sense. So these read-only views, they are great for exploration. You can quickly see what the design is about, but they're not ideal for documentation. So we need to add something new. So we have these, we went and did some research. We did one operation on this diagram, which is just grouping wires together, and suddenly you start to see structures. So a block over here, 2 blocks here, and a big block here. And so with just one operation, we could do quite a few things. So we thought, with these read-only views, we took all of the freedom away from the designer. Maybe we should give some back, let him edit his graphical views again. So we asked the clients, what do you need? How would you like to edit all of this? And then we created a mock-up of that, and we ended up with this. Not ideal. Doesn't really match with our goals either. So the most important goal is that we can filter your diagram down, so that's usable for documentation. And it should simplify collaboration, so that I can make one diagram and then all of my colleagues can use it. Or we can both work on a diagram together, so version control. Which means that whatever solution we have needs to be serializable and mergeable, and also reproducible so that same inputs get the same output. And of course, it's still used for documentation, still used for exploration. So we should be able to highlight the important parts. So we updated our view a little bit, still have your HDL code, can still compile it, get your feedback, still generate your read-only views and navigate back and forth, but we added a DSL. We might have also opted for a key value mapping, but then you just end up with the UI example, but in text. So still way too many options. And implementing this DSL wasn't extremely hard because we have Xtext, so it allows us to have our HDL code talk to the DSL. We can have autocomplete of things defined in the HDL code. We have hovers. And it also allows us to, for example, have formatting in DSL, which is important to normalize your DSL, which will be used in version control. And the most important part is that the errors in your HDL code propagate to the DSL, which means that your documentation can evolve with your source code. And then, of course, the DSL can also be compiled. You get errors, navigate back. You create configured graphical views, and then navigate back and forth as well. And there are a few more advantages to a DSL that is used in a separate file. So with 0 source changes, you can add documentation to your project. And you can also have multiple views for one source. So a designer needs to look at data flow a lot of the times, but sometimes he needs a clocking and reset structure. So you just create 2 configuration files and you're off. And you can also generate new files, for example, grouping all of the wires between 2 blocks, as I will show in a demo in a little bit. And this approach worked for us because our clients are engineers, they are domain experts, and some of them even know Xtext, so yeah, this works. Might not work for everyone. But let's get started with a demo. Okay. So over here you can see Sigasi Studio. So it's obviously Eclipse based. I'm not on the right file. There you go. So as I'm the formatting guy, the first thing I have to show you, of course, is formatting. So right click over here and then go to Source, Formatting. And there you go, everything is nice and aligned on colons and so on. Now we have basic syntax highlighting. We also do syntax errors, so I is unknown. We have basic linting, so a double equal is not something that exists in VHDL. You should use a single equals. And we have some more linting, so for example, a data out is a signal, not a variable, so you should use less than equal. Okay, please just fix this for me. So this character changed. We also have some autocomplete, which you get by analyzing all of the source code. For example, just fill in a case statement, switch case for the state. And then you can hover over things. So for example, this clock is an import of the type standard logic, and it has a comment, this is the main clock. And if I control click on it, we go to the definition, we can control click on the standard logic, go to that definition, and so on. So that's Sigasi, but you came here for graphics, so let's show you a few graphics. Don't care about saving. So this test bench, let's start off with the most simple view, which is a dependency view. Dependencies, there you go. So this used to be one of the views that was still using Zest, and I changed it 2 months ago, I think. So you can have some interaction with your source, you double click on .vhd, and it opens up .vhd. Okay. And in this code, you can see there's a switch case statement over here, and a switch case statement that's actually just a state diagram. So let's show this in the state machine view. There you go. So we analyze the code, we generate a state machine from it, and then you can just double click on states to go to them, double click on conditions, or on your comments to go back and forth to the code. You can also disable those, or you can do all of the zooming things. And then the more important one is block diagrams. So let's open up this block diagram file. So this is one I showed you in the examples. Let's show it in a block diagram view. So show in block diagram. Make it zoom. Okay, so it selects the block. You can still double click and stuff. So let's try to configure this block diagram. So we changed files, and here we have, okay, this is a diagram in the library work for the entity foobar and architecture RTL. So what you first see over here is a little ball, this is like an assignment, while those blocks, they are instantiations, and those are important for the structure of your design. So we only want to see structure. Let's get rid of the little ball. There you go. And then, okay, let's just group the middle because, well, those belong together. There you go. And here I just type block 2, block 3. Maybe what I want to do is use autocomplete, so define a block group called middle and just choose a regex, and which would be block 2 and 3. Save that, comment the other one out, and if you hover over it, you see, okay, this block 2 and 3. I can format this code again by pressing Command-Shift-F, and then we can just continue on. So these regexes were very important because you have a lot of wires in most of your designs, and if you have to, even with autocomplete, select all of them, it takes ages. It's quite confusing as well. So you can collapse a few wires, so that's this one over here. You can navigate to it. You can hide the port, which is over here. There you go. You can also color some blocks to highlight them and hide a few more ports. We can then color these blocks in the middle. There you go. You could also use a regex over here so you don't have to type everything. And while the middle is not important, let's just collapse it. There you go. And you can navigate back to it as well. And then finally, yeah, sure, make this block red. Cool, so now I have my diagram. It's good for documentation and navigation. Let's navigate to this block. Oh, the diagram changes. That's quite annoying. So let's go back, pin this diagram, and then when I double click on it, it stays in view. It doesn't change, but it does listen to my actual source code. So if we get rid of block 4, it updates. While it doesn't do that when I update random code. So that does nothing. We can do the same for state machines. So over here, I have a state machine. Let's just comment this out and open this in the state machine view. There you go. So this is the basic state machine we saw before. You can still have your labels. But we can just go ahead and group a few things and put them in colors. There you go. And also those can be collapsed and hidden and so on. And you can double click as well. And I also said that being a separate file is quite good because you can create the files automatically. So if I open up this block diagram, there you go, unpin this, you see that here we have 2 wires going from block A to B, and same for here, block C to D. If I just click on this little button, group all wires between blocks, we create a file which created wire groups for this. And if I zoom in, you see this has become fatter and in gray. So it grouped the buses together. Yeah, so that's the graphics configuration file. And there's a lot more options we could add, but this does most of what the clients want at the time. So let's get back to the presentation. There you go. Okay. Having seen the demo, you might wonder how it works because you didn't see it crash, it all worked. So testing of the DSL is quite easy. You can just use Extract for that, and it's fully covered. And for the UI, we use Alk, Klite. We just assume that the frameworks works. Then we have SVG export, which is used to verify that we're drawing the right things, that things are collapsed, and so on. And that's quite a challenge because the size of the nodes depends on the text, and the size of the text depends on your rendering, which is different on every machine. So our tests work on single machines, but not necessarily on all of them. So if you have a solution for that, please tell me afterwards. So in conclusion, we think you should be using graphical views, not graphical editors, because they come with way too much problems. And you shouldn't use a one-on-one projection because that's too cluttered, there's no focus. And most of the time you want to filter something out or allow your clients to do so. And we're also quite happy with the technologies we chose, so ELK, Xtext, Eclipse. They allowed us to focus on a real problem, so how do we get the designers their graphics back? And it gave us a lot of free features like the autocomplete, so configuration files can be written mostly just by autocomplete. If you liked this session, disliked it, please vote for it at eclipsecon.org and do the same for all the other presentations you go to. If you have any more questions, go ahead and ask them now. No questions? Okay, then you can go enjoy the food and drinks.